Hello, and welcome back to the course on thermodynamics. We are still on the unit on the first law of thermodynamics. So before we proceed with this lesson, let us first recall some of the concepts that we have discussed. So we have discussed about molar heat capacities in unit number 1 when we discussed about uh, the quantity of heat involved in changing the temperature of an object or material. We also have discussed about molar heat capacities in Unit 2 when we discuss about the heat capacities of uh, the molecular thermal properties of matter. So in the previous lessons, we discussed about the first law of thermodynamics and the kinds of thermodynamic processes. And we have, in passing, introduced the concepts of heat capacities at constant volume in isochoric process and heat capacity at constant pressure for isobaric processes. So in this lesson, we will be focusing on the heat capacities of ideal gas, the CP and CV, heat capacity at constant pressure and heat capacity at constant volume, and find their relationship. How are they related? So let us start. So if you have a constant volume process, such as an isochoric process, so you have a fixed container volume. So see here we have n moles of ideal gas in a fixed volume. We added heat to it, and the temperature changes. So in this case, the change in internal energy, assuming this is ideal gas, is just equal to NCV delta T. Now, if you have a constant pressure process, such as an isobaric process, in this case, the pressure is maintained. Uh, it is maintained at a certain. The pressure is maintained at a certain pressure by letting the gas expand. So you have now an expandable volume. So you still have n moles of ideal gas, and in this case, the change in internal energy is just the heat added minus the work. So the heat added here is just NCP at constant pressure delta T minus P times change in volume. Now, uh, take note that we have this emphasized this before in the previous lesson, that the change in internal energy of the ideal gas doesn't actually depend on volume or pressure. It actually just depends on temperature. So looking at here at this relationship, and if we recall ideal gas law, at constant pressure, if the volume is changing, only the temperature is changing. So P times change in volume is equal to NR times change in temperature. This is from the ideal gas law. So if we replace this by this one, so we get this expression. Now, you will notice that all of the terms contains N and change in temperature, N and change in temperature. If we divide both sides of this equation by N and the change in temperature, we get the relationship between the heat capacity at constant volume, the heat capacity at constant pressure, and they're actually related to R, the gas constant, meaning the unit for heat capacity and heat at constant volume and at constant pressure is just the same as the uh, gas constants units, joules per mole Kelvin. So the ratio between these two, the heat capacity at constant pressure of the heat capacity at constant volume, is what we call the gamma factor. And this is always greater than 1 because Cp is always greater than Cv. So actually, if you rewrite this, if you write this in terms of Cp, you will actually get Cp is equal to, if you transpose R to the other side of the equation, then you will get Cv plus R. So this makes Cp greater than Cv because Cp is just Cv plus R. So Cp is always greater than Cv, the heat capacity at constant volume. Okay. So these are the molar heat capacity values for different gases. So you will notice that the relationship between Cp and Cv are accurate for monoatomic and diatomic gases. So Cv for monatomic gases is 12.47. For the diatomic, it changes slightly. Similar with Cp, Cp and Cv values are accurate for monatomic gases, but not so accurate as you go to diatomic gases. But the difference between Cp and Cv, it's almost the same, 8.31 joules per mole Kelvin. Because the difference between Cp and Cv, this is the gas constant, right? This is equal to R, 8.315 or 3145 or round off 8.31 joules per mole Kelvin. So you will also notice here the ratios. So for monatomic gases, the gamma ratio is 1.67. And for diatomic gases, the ratio is 1.41 or 1.40 or round off 1.4. So if you have an ideal gas with a gamma ratio of 1.4, that means it's a diatomic gas. If you have an ideal gas with a gamma ratio of 1.67, that is a monatomic gas. Okay. So let's have an example. So this is an example of cooling your room. So a typical dorm room or bedroom contains about 2,500 moles of air. Find the change in the internal energy of this much air when it is cooled from 35 degrees Celsius to 26 degrees Celsius at a constant pressure of 1 atm. So treat air as an ideal gas with gamma is equal to 1.4. So in this case, we are uh, trying to treat air as a gas with ideal gas with gamma of 1.4. So it's like an ideal diatomic gas. Okay, so in order to solve for the change in internal energy, since the change in internal energy for an ideal gas only depends on N, Cv, and the change in temperature, then we can now solve this problem if we know the heat capacity at constant volume of this ideal gas. So this is the number of moles. We have 2,500. Change in temperature is from, the final is 26, initial is 35. So this is a negative change in temperature. So we are only given with gamma, but we know that gamma is equal to Cp over Cv. So we cross multiply Cv to gamma, and we have gamma Cv is equal to Cp. But Cp is equal to Cv plus R. So we are now left with one unknown instead of two unknowns. So the only unknown here is just Cv. So group your Cv and solve for Cv. So Cv is R over gamma minus 1. So R is 8.3145 or 8.31 if you want to round off joules per mole Kelvin over gamma is 1.40 minus 1. And you get Cv of 20.79 joules per mole Kelvin. So actually, this is pretty much the heat capacity at constant volume for diatomic gases. It's 20.8 round off joules per mole Kelvin. So we use this value for Cv, and then we have this change in internal energy. Of course, it's negative because the temperature is decreasing. So a decreasing temperature means a decreasing internal energy. Okay. So that is it for this lesson on the heat capacities of ideal gases. So we will focus mainly our discussion on ideal gases. And in fact, in the last lesson for this unit, we will focus on ideal gases and on the adiabatic process. So I will see you again on the last lesson for this unit.